So let's start with today's lecture. So are there questions from last time? Yeah.
Yes, the last relation of yesterday works for any distribution.
Which one? Yes, the work distribution you mean?
Yes, the
Crooks.
Hanno-Sass equality.
Yes, it works for any distribution.
You can put any non-equilibrium.
Any non-equilibrium distribution. Absolutely.
Okay.
It's very general. You mean the this one, no, that I defined, this phi. Yeah, this can be anything. Any other question? Okay, so maybe then we go on with where we left off. So today and tomorrow we will do quantum synchronization, just to see, what happens when you have a quantum system and what does it mean to have synchronization in quantum systems. So we will see how does the concept of limit cycle that we saw a lot generalizes to a quantum system. What does it mean to have so the first problem that we face is that of a phase space. Okay, so as we talked about it when we discussed about limit cycle, so these are closed orbits in the phase space. Okay, so but now for a quantum system, okay, so the main problem is that suppose you have, so in the classical setting the picture was the following, that you had a set of equations for the dynamical variables. Okay, and we found that you can of course represent the state of the system by a point in this n-dimensional phase space. Let's say alpha goes from 1 to up to n. So this is an n-dimensional phase space, x1, x2, x3, etc., xn, where this is a state of the system, and a limit cycle is defined as a closed orbit in this phase space that has the equation of motion. I mean, on the limit cycle, this is the time evolution of the phase corresponding to the limit cycle. And we said that, okay, it also applies to close by trajectories. If it is a stable limit cycle, so close by trajectories are attracted towards it and so on. How do we generalize it to a quantum system? So the first problem is that in the quantum case, the underlying dynamics is Schrodinger equation. And what is the, how do you define a phase space? I mean, what are these variables? Okay, so that is not a priori clear. It has to be done somewhat differently. So before I move on, I need to know how much you know about quantum mechanics of harmonic oscillators. Quantum harmonic oscillators, the ladder of the creation annihilation operator, coherent state. I need I need to know whether you know about coherent states and what are the properties of a coherent state. If you don't know, then tell me. Then what I can do is that I can just give you a brief introduction. But in the assignments as well as in the lecture notes, you will find somewhat more detailed discussion. But you need to read from a standard quantum mechanics book about coherent states. Probably Sakura is a good book, or Cohen-Tannoji. I mean, I think these are standard books. How many of you know about coherent states of a quantum harmonic oscillator? So quite, but okay. Okay, so let me then quickly review. I will not derive any equation because these are very standard stuff, and if I start deriving all those equations, then it will just. Okay, let me first, before I go to coherent state, let me first tell you why do I need a quantum harmonic oscillator. You recall the equation that we had written down for the van der Pol oscillator. Okay, this was the equation of a van der Pol oscillator that admitted a limit cycle. Okay, why do we want limit cycle? Because ultimately in the classical case, our starting point was one limit cycle and then many limit cycles and then synchronization among those limit cycles. So in the classical case, just as we had started with one limit cycle, so in the quantum case also we need to know what does it mean to have one limit cycle, and then we'll talk about interaction between them and so on and so forth. Okay, so this was the van der Pol oscillator. So if you look at it, you see that this is the part that corresponds to a simple harmonic oscillator. Okay, a simple harmonic oscillator which is closed, so to say, in the sense that there is no damping or anything. So it is just the dynamics corresponding to the Hamiltonian of a simple harmonic oscillator. And this one is the damping part. Okay, it can be positive or negative depending on the sign of x square with respect to 1. So therefore this system, it looks like it is like a simple harmonic oscillator, a Hamiltonian system, which is interacting with some kind of a bath. Okay, and the bath is inducing some noise, some dissipation in the system. There is no noise term, there is no eta, but at least you get the feel that it somewhat rings a bell, that it has to do with a Hamiltonian system in contact with some bath or some environment that is introducing some dissipation in the system. Okay, so then
Can you repeat your last sentences about that?
Okay, you see, okay, so this part x double dot plus omega square x equal to 0, this equation derives from a Hamiltonian, right? I mean the Hamiltonian is just the simple harmonic oscillator Hamiltonian. So if you take this equation and you say x dot is p by m, these are the Hamilton equations. You combine them, you get this equation. Okay? You will never get this part. The damping, it cannot be derived from Hamilton because the Hamiltonian dynamics will conserve energy, and this term will not conserve energy. Okay, it will energy may increase, decrease, but it will not remain the same. So therefore you can think of it this way, that this part, it looks like there is a simple harmonic oscillator which is interacting with the environment or a bath, and the bath is inducing some dissipation into the introducing some dissipation in the dynamics of the system. You know about canonical ensemble, grand canonical ensemble. Canonical ensemble, you know that you have a system which is not isolated, which is exchanging energy with a bath, and therefore the energy of the system itself is not conserved as a function of time. Here the situation is somewhat similar. Okay, this term doesn't allow energy to be conserved, so I can attribute it to some interaction of the system with the bath or environment. Okay, so then we want to take it off from here. What we want to do is, given this classical setting, we want to describe or consider first the situation where you have a quantum harmonic oscillator which is interacting with a bath. Okay. So in the classical case, we know how to model such a dynamics. Okay, typically what you do is that you write down a Langevin equation. You say that in the classical case, let's say you know about Langevin equation, right? Okay, so Langevin equation typically, let's say for this equation, or let's say for simple harmonic oscillator, this could be one possibility. Okay, this is we looked at a Langevin equation, no, for the noisy Kuramoto model. So, now the question is, how do I write such an equation for a quantum harmonic oscillator? By the way, before I move on, I see that for a system which is classical system which is interacting with a bath, there are two equivalent ways in which you can study the system. One is this trajectory approach. You want to know how does the position of the particle, the dynamical variables of the particle, how do they update in time, okay. So you write down a Langevin equation. There is another approach, equivalent approach. Can somebody tell me what is the other way in which you can study a system which is interacting with a heat path? This is the trajectory approach. There is another approach. Distribution or Fokker-Planck equation. So you want to know how does the probability to obtain x at time t, how does it change as a function of time, and you write down a Fokker-Planck equation, okay. So these two are equivalent approach. I mean, either you look at individual trajectories, more generally master equation approach, okay. So either you look at individual trajectories to ask how does the position of the particle change as a function of time, and depending on the position values that you get, you can draw the histogram, okay. So this is this approach. Secondly, second approach is you directly write down an equation of motion for the histogram, okay. This is the Fokker-Planck or more generally master equation approach, where you look at the ways in which this probability distribution change as a function of time. You know these things, right? I mean, master equation and yes or no? Okay. Okay. So then we have to see, you know, what is the, how do I write down a Langevin equation or a Fokker-Planck equation for this sort of setting? It turns out that the equation that is equivalent of Fokker-Planck, or more precisely master equation for classical system, is what is known as the Lindblad equation, okay, which will describe a quantum harmonic oscillator interacting with a heat bath, with some bath, okay, not necessarily heat bath, it could be a bath of phonons or photons and so on. Okay. So before I go there, the motivation is clear, right? This is a system interacting with a bath. I can study it using Langevin or Fokker-Planck equation. I want to generalize this to a quantum setting. You have a quantum harmonic oscillator which is interacting with a bath. What are the variables that I should be looking at, and how do they change as a function of time? What is the equation that I write down, which is equivalent of either the Langevin or the Fokker-Planck equation, okay? So, like again a question, how many of you know about density operator, density matrix, density operator? So, okay. Okay, so somehow you are half raised. So does that mean that you have only half knowledge of it, or you do like this? Do like this or this? Or it doesn't make any difference, okay. Okay, so not many of you know about it. So quickly, let me just quickly, very quickly tell you about this. See, this is the issue with quantum that you need to have, okay, but anyway, let me try, okay. Okay, so now we are dealing with a quantum system, okay. Quantum system given by some Hamiltonian, okay, and let's say it's a system composed of many particles. So these are the positions of the particles, let's say n degrees of freedom, okay, and there is some Hamiltonian. So what is the way to describe a quantum system? You don't talk about the positions of the individual particles. Instead, you talk about a wave function that refers. So this is one guy that relates to the complete system, such that this wave function is a function of time, such that the time evolution is given by the Schrödinger equation. Okay. So just as in the classical case, we were talking about Hamilton equations and energy being conserved as a function of time, okay. And the Hamilton equations describe a closed system, a system which is not interacting with a bath. So in this case also I am talking about a closed quantum system. So this is how the wave function, wave vector evolves as a function of time. And if you want, what is the interpretation of this guy? The interpretation is the following, that if I look at this quantity, okay, I know I hope you know about this Bra and Ket, right? I mean, these are objects living in the Hilbert space of the system. Think of them as vectors, okay? There are other properties. So if you take this product, this is ket, this is bra, so then you get a function which is a function of all the coordinates of the particles. This still doesn't have any physical interpretation as such unless you take the mod of it. Because this is a complex quantity, so you may take the mod of it. And now this one has a physical interpretation. This one says, what is this guy? This gives you the probability density of finding the system in a state in which there is one particle at location x1, another at x2 and so on. Okay? So this one has a physical interpretation. So I can study the system either in terms of the wave vector, that is to say that I say that I initially prepare the system in a certain state, which is this, or equivalently, okay, there should be a t here. The interpretation is this gives you the probability density to find the system at time t in a state in which there is a particle at x1 and x2 and x3 and so on. So either I study the system in terms of this Schrodinger equation by saying that there is an initial state in which an initial state which is characterized by this wave vector or this function x1, x2, xn t equal to 0. Okay, this I have to give as an input and then I solve this equation subject to this initial condition. So this is a linear first order differential equation in time. So therefore this has a very simple solution. It says that psi of t is equal to e to the minus ht by h bar of psi of 0. So the situation has an exact parallel in classical mechanics, that you give me the initial state, I will give you the final state. You give me the initial state, I will give you the final state. Okay. So this is one way of looking at the dynamics. That is to say that I look at the state of the system at a later time given this initial state. What do I do with such a state? Well, what I am interested in eventually will be I will be interested in the value of an observable at time t. Some observable, let's say I want to know what is the kinetic energy of the system, what is the temperature of the system, this, that, etc. at time t. So what I would do is that corresponding to every observable, there is a Hermitian operator that I have to construct, and once I know this Hermitian operator, then what I have to compute is I have to compute the quantum expectation of this guy, which is by definition equal to psi of t O psi of t. This is what I will measure, because in quantum mechanics what happens is that if I give you the state and the operator, and when I act on the state by the operator, I may get many different answers, because what will happen is that when O acts on psi of t, then what I will get is that I will get, let's say O is being a Hermitian operator, it has eigenvalues, let's say lambda 1, lambda 2, etc. So then when I act on it, in some measurements I may get the value lambda 1, in some measurements I may get the value lambda 2 and so on. And when I take the average of this guy, the quantity that I get is this quantum expectation. So that's why it is called expectation value, mean value, average value. Somehow we don't use the word average or mean, we say expectation. This picture is, you know, right? This is the picture of quantum measurement, that in the case of classical mechanics, when you measure, you get just one value, that's it. There is no possibility of getting many values. But here I may get many values depending on, when I do the measurement once, I get eigenvalue lambda 1, and the system will collapse into the corresponding eigenstate, or I may get lambda 2 and lambda 3 and lambda 4. So I have an uncertainty associated with the outcome of a measurement. I am not pretty sure which is the value. I will not get one value, I may get many different values, and the average of all the values is what is given by the quantum expectation. You can do this calculation quite easily. Just do the classical expectation, lambda I times what is the probability of getting lambda I. So that would be the inner product of the corresponding eigenstate with psi of t, and you can write it exactly like this. Okay, this is a simple exercise, so I hope you know, so I am skipping the details. Okay. So this is one way of studying the system. I look at the wave vector at a later time, given the wave vector at time t equal to 0, and if I want to know the average value of an observable, then I need to do this, I need to compute this quantum expectation. So this is, let me call it, this is the wave vector approach. But there is an equivalent approach that one can look at, that is to say, not to look at the time evolution of the wave vector. In this same setting, one can define a quantity called the density operator. So this is defined this way. The two approaches are exactly equivalent. Okay. So here what I do is that instead of looking at the operator, this is like a, this is like a column vector. No? Instead of that, I look at the time evolution of a matrix constructed out of the column vector, and I know how psi of t evolves as a function of time. I know that I h bar del psi t del t is equal to h of psi t. Okay, so I can just plug this in here. The thing that I see is that, okay, rho is explicitly time dependent because the state is changing. So therefore I can write down a time evolution equation for rho. Okay, and this will be, I hope I am getting the sign right. Okay, this is a simple exercise. You just plug it in here. You will get once h from this side, once h from that side, and you can write it in terms of a commutator. Okay. In this picture, how do I compute the expectation value? The expectation value of any operator O in this picture is computed by multiplying rho with the operator O corresponding to the observable that I have, and I then have to take the trace of it. So these two approaches are exactly equivalent. There is nothing that is different from this than compared to that. Okay, I hope this much maybe this one is more familiar, but the density operator approach is somewhat less familiar. But these two are exactly equivalent. Okay. The advantage with this approach is that this one allows you to generalize this situation to a case in which the initial state is not one state but a statistical mixture of many different states, which is difficult to do here. What do I mean by that? So let me just quickly tell you. So when I know the initial state for sure, this is the precise state in which the system is in, then there are two ways to study the system. Either I say state at time t is e to the minus iht by h bar psi of 0, and then I compute the quantum expectation of any operator as psi of t, O psi of t. Or second approach is I construct the density operator. Okay, no, I construct the initial density operator. Okay, because this is the input, so I can construct the initial density operator and then solve this equation to obtain the density operator at a later time. And once I know the density operator, then this guy is just given by trace of rho O. Sometimes I am putting a hat, sometimes I am not putting a hat. Okay, for rho I am putting a hat. Okay. H is, by the way, an operator, so maybe I should put a hat. Eventually I will get rid of the hats, because you may grumble that on this side I have an operator, on this side I don't have. Okay. Okay, so this is easy. But the second situation is, it may so happen that the initial state, for the initial condition, I cannot say for sure that the system is precisely in this wave vector state, in this state. It may so happen that the initial state itself has got initial state has got some element of randomness, in the sense I can only say that with P1 probability the system is in state, let me put 1 here. With P1 probability the system is in state psi 1 0, with P2 probability the system is in state psi 2 0, and so on. That is, there is an element of uncertainty as to which state the system is in at time t equal to 0 itself. Here there was no uncertainty. I could say for sure that the system is in this state. Here there are many possibilities. Then how do I do this thing? Clearly, this approach is very difficult to now implement, because what will you write down for the state of the system? The state of the system, I cannot write down an equation of the following sort. Psi of t is P1 times psi 1 0 plus P2 times psi 2 0. This I cannot do. Why? Because you see, these are complex numbers, okay? So linear combination of a state which is constructed by taking linear combination of other states, doesn't make sense, okay? So what is the way? So the first approach, it doesn't work out. Let me call it approach 1. So this is approach 1. It doesn't work. But approach 2 is quite easy to implement now, because now, by the way, I am tempted to give you an example that I remember having read in Sakurai's book. He says, okay, let's say I take an examination. I mean, there's a class of students and I take examination, and I know that all the students have gotten above 80% in the test, okay, which I hope you will get in the exam that will happen on Friday. So then I know that, okay, everyone is in one state. Everyone has got above 80%. But suppose I say that 40% of the students have gotten, have secured the marks 60%. So 40% of students have got, let's say, 60 out of 100, and 60% have got 20 out of 100. Okay? Which is, of course, not I would hope to see on Friday. But anyways, so then what do I say about the state of this class? Do I say it is 40% in state 60 and 60% in state 20? No, doesn't make any sense. Because linear combination of student states, I mean, what does it mean? Doesn't make any sense. Okay? Instead, in this approach 2, it is quite easy to do. So I just write down the density operator. Now the density operator will be, the density operator will be this guy, provided the system is in state I. Maybe you are unable to see from here. Maybe I should move up. Okay. Maybe I draw a line here as I was drawing this. Okay. So I am here. Approach 2. Approach 2, what I do is that I say, what is my initial density operator? The initial density operator would have been psi I 0 psi I 0 if the system were in this particular state. And what is the probability that the system is in this particular state? It is Pi. Pi. So therefore, this is going to be the density operator of the system. You see, this formula is very general because I can easily take this into account with the help of that formula. Here what I will do, I will say that the system is precisely in this state. So therefore, Pi will be equal to 1 for the state the system is in, and it is equal to 0 for the remaining states. So this is very general. Is this definition clear? That this is going to be the density operator if the system happened to be in this state psi I 0, but then it has possibilities to remain in other states as well. So I take a statistical mixture of all possible states. Okay? And then the rest of it is exactly the same. In this picture again I can write down the time evolution operator for the density operator. It will again satisfy the same equation. So I just solve this equation subject to this initial condition, and then if I want to know the quantum expectation of an operator at a later time t, I do trace of rho O. Okay, so this is the density operator approach, which is applicable, particularly applicable when the initial state is a statistical mixture of many different states. Okay. How do I get this equation? Well, how do I get it? Is that each of these psi i's will evolve following the same Schrodinger equation. So I just use this equation here. I just say that because each of these psi i's is a valid state of the system, so each one of them will evolve according to the same Schrodinger equation. So what I do is that I take rho of t and I take the time derivative. I'll use the Schrodinger equation. I'll get this one. Okay. So these are this equation, or the Schrodinger equation. These equations apply when the system is closed. That is to say that the evolution is such that it is entirely governed by the Hamiltonian, and the evolution is such that it is unitary evolution. Unitary evolution in the sense that, okay, so if I solve this equation, I will get psi I t to be given in terms of a unitary operator. What is this unitary operator? It is e to the minus I h t by h bar. What is the definition of a unitary operator? How do you define a unitary operator? If U is a unitary operator, then what property should it satisfy? Huh? Equal to? U dagger is equal to U dagger U is 1. Okay. You can check that this exactly satisfies this. U dagger is e to the I h t by h bar, and because h is Hermitian, so h dagger is h, and U inverse is also e to the power I h t. So it's unitary evolution. But now the question is, what happens if the system is interacting with a bath? So you can think of the Schrodinger equation as the equivalent of Hamilton equations. This is Hamilton equations, and now when the system is interacting with the bath, in the classical case you had Langevin equation. So how do I generalize the Hamilton equation? Okay. In the classical case corresponding to the Hamilton equations of motion, what is the equation that is satisfied by the probability distribution? Certainly not Fokker-Planck. So what is the equation that is there? We talked about it, but you must have read it in statistical mechanics, electrodynamics, fluid dynamics, everywhere. Continuity equation. So in the classical case, if I have to draw a table, I would say that, okay, this is classical mechanics. Okay. So when the system is closed, then you have Hamilton equations. Hamilton equations for the trajectories, or equivalently equation of continuity for the histogram. Liouville equation, if you want to talk about the phase space density. Let me do a better job. Let me, oh, this one is wet. Actually, this continuity equation has a name. Can you tell me what is the, let me do a better job. Okay? Huh.
What is the main difference between the quantum, the open quantum system and closed one? What's
Huh.
the exact relation?
Yeah, I haven't come yet to close, to open. So therefore, please bear with quantum mechanics. Let's first talk about the closed sector, because closed sector is easy to do. Okay. Let me see like this. So in the closed sector, what I have in the classical mechanics is, I have the Hamilton equations. Hamilton equations for the positions and the momenta. Okay. Similarly, on the quantum side, I have the Schrödinger equation for the wave vector. So this is the trajectory approach. Okay. And what is the other approach? The histogram approach. So in the classical case, what you do is that you say that every such configuration or every such collection of real numbers defines for me a point in the phase space. So I have a phase space where each such configuration is a point, and then I define what is known as the phase space density, which is x pi t, and this satisfies just check this sign. I think this plus rho h rho. Okay, this is what is known as the Liouville equation. Can somebody quickly check if I got the sign right? I hope it is right, del rho del t plus rho h. I think it is right. Okay. In the quantum case, what do I do? Instead of defining the phase space density, I have the density operator. Okay. And the time evolution equation is del rho del t is equal to minus I by h bar of h rho. In the classical case, if I have to talk about an observable, space there, so maybe I do like this. If I want to know the value of an observable, the average value of an observable at time t, so what I do is I do O xi pi rho xi pi dxi dpi. So I have to integrate over all I. Okay. I write too big, no? So therefore I eat up space in no time. Is pi I dxi dpi integration of O, which is a function of xi and pi into rho, which is a function of xi and pi, comma t. This I do in classical. In the quantum I do exactly the same. That is, if I want to know the average value, so then I have to do this, which is nothing but trace of rho times O. So everything has a parallel, okay? Every quantity that you come across in classical mechanics has a parallel. You just call it differently. Here you refer to rho as the phase space density. Here, instead of calling it the phase space density, you call it the density operator. Here the phase space density evolves according to the continuity equation, which is referred to in the classical case as a Liouville equation. In the quantum case, you have the corresponding quantum Liouville equation. This has a name, it is called von Neumann equation. Instead of calling it quantum, I guess von Neumann was the first one to get it. Here, if I want to know the average value of an observable, I need to multiply the observable by rho, the phase space density, and integrate. Here, if I have to know the average value of an observable, what I need to do is multiply rho by O and then take the trace. So this is for closed systems. Okay. Now what happens if you have an open system? By open, what I mean is that in the classical setting, the equations of motion are not given by Hamilton equations. Okay. So what is the simplest model that you can come up with for open systems, open classical system? A Langevin equation. So what you do is that you take the Hamilton equations and then you introduce a dissipation term and a noise term, and typically the noise term is taken to be Gaussian white noise. So instead of Hamilton equations, you have Langevin equations instead of the Liouville equation. So Langevin equation, it corresponds to Hamilton equations in the sense that you introduce noise and dissipation, and similarly for Liouville equation for the histogram, instead now you have the master equation, which in particular limit will reduce to the Fokker-Blank equation. What is the scenario now here? Okay, here for example, instead of Liouville equation, you have master equation. Here, instead of the von Neumann equation, you now have the quantum master equation. Okay, and so this has a name. This is called the Lindblad equation. So how does it look like? Let me see. Just don't want to make the yeah. Plus some terms that would mimic the interaction of the system with the ambience, with the environment. But now I have to be careful that these terms cannot be just arbitrary. They have to be such that something has to be preserved under the time evolution. What is it? Rho, when I introduced rho has a basic property. Why? Rho has to have a basic property. You see, when I am computing the average, it seems as though rho is like a probability distribution. Okay, because when I take the average of a quantity, what I do is that I take the quantity, I multiply it by probability, and then I integrate. It has the same form. Okay, instead of integrating, I am doing trace operation. Simply because I am dealing with, these are discrete numbers and so on. So what is the basic property that I should have? The basic property that I should have is, if this has the interpretation of a probability, then trace of rho has to be equal to 1. This is exactly the same that I have here. This rho, the phase space density is normalized to 1, so therefore trace of rho is also equal to 1. So here when I write down the time evolution equation in presence of a heat bath or some bath and so on, I have to write down such terms, these terms, they have to be written in such a way that the trace of rho is equal to 1 at all times. Okay. Now this is a very long derivation of how to get this form of the equation. Of course you cannot do it in full generality, you have to invoke approximation. So let's see, before I go to the quantum case, let me ask some of you, how would you write down the time evolution equation for the phase space density of a system which is in contact with a heat bath? You need to invoke some basic assumptions, otherwise you cannot do. What is the basic assumption? What are the basic assumptions that you do for the classical case? So I have two entities, this guy and that guy, and they are interacting, and I want to write down an equation of motion for this guy. See, I have to have some time scale separation, right? Because if there is no time scale separation, I want to know about the state of this system, I better know the state of this system. But if I want to know the state of this system, I better know the state of this system. Then how do I make progress? I can only make progress if I say that the bath, typically that's what you do when you do Langevin equation. You say that the bath, it is modeling some fast processes. The bath is already in a stationary state, okay? So the bath properties are not changing as a function of time, while the system is changing as a function of time rather slowly, and so there is a time scale separation. That's how you do Langevin equation, master equation, Fokker-Planck equation. In the quantum case also you have to do something similar. Namely that the bath is already, has time independent properties while the system is changing slowly. So there is a time scale separation. You have to invoke other approximations which are also there in the classical setting, Markovian evolution, etc. Okay? So the equation that you get is rather complicated. So let me write it down. There is a derivation of this equation given in the notes. There are many ways to derive this equation. There is a very long derivation that you find in textbooks on open quantum systems. Okay, I will give you the reference. Okay, there's a book by Carmichael which is good. Then there's a book by Scully. Okay, these are some of the references. One is this. There's a book by Scully. I think it's called Quantum Optics or something like that. I don't remember. Then there's a book by Gardiner and Peter Zoller. And then there is a book by Michel Preuer and Petruccino. Maybe the Italians can help me with the spelling. Is this the way it is written? Petruccino? 2C? G is 2C, right? Okay. So these are the standard references. And how does this equation look like? So this looks like this. Of course, this part is the unitary evolution of the closed quantum part. Plus, you have to add terms that would model the interaction of the system with the heat bath. Now, this is left entirely to your discretion. What sort of dynamical processes you want to model by coupling the system with the heat bath, okay? So let me take, for example, the case of a quantum harmonic oscillator and say that, so let's take a quantum harmonic oscillator. Actually, before, perhaps I'm, jumping steps. Up till this now, like everything is fine. You know what is the difference between classical and quantum? I mean, besides the general thing, classical is classical and quantum is quantum, but beyond that, huh? Hey.
Why can't we add the interaction part in the Hamiltonian?
Yeah, you can. This Hamiltonian is. You mean to say why? Okay, good question. Okay, Okay, that's a bit technical question. Let me answer it. But before that, are there simpler questions for me? Okay. See, what you would like to do is, you would actually like to add the interaction part, but then you have this system. Okay, this is interacting. This is my system. This is the bath. Okay. Ideally, what I should do is to write down the time evolution for the density operator of the entire set, right? So let me call it rho total. Okay. Then of course this one will be given by, as you may imagine, system plus bath. That's a closed quantum system. Yeah, because bath means like anything and everything that is external to the system. So I can include the entire universe here. So the entire system, of course, will have unitary evolution. No problem. But see, what I am interested in is the description of the system variables. So what I need to do is I need to find out the density operator of the system and only the system. So what I do is that I take rho total and then do what? If I want to know the density operator of only the system and I know the density operator of the entire system plus bath, what do I need to do here? Trace out the bath degrees of freedom. It is like a marginal distribution. You have a probability distribution of 50,000 variables. You are interested in only 10 variables. So you take the 50,000 guys and integrate out 50,000 minus 10, which is 4990. Okay? So it's the same. So what I need to do is, I need to take this equation and then trace over the bath degrees of freedom, where this H total will have 3 contributions. H total will have a system contribution, a bath contribution, and an interaction. See, the left hand side is quite easy to deal with, because if I integrate out the bath degrees of freedom, it's okay, no problem. When I try to do it here, okay, here I don't have to do anything, because here it is already, this refers only to the system, this refers only to the bath. Here I will encounter problems, because these involve cross terms, terms that lead to an interaction between a bath degree of freedom and a system degree of freedom. And I cannot do it in full generality unless I assume some time scale separation. Okay? What I typically assume is that, I say that initially the system is in a product state. That is to say that initially rho total 0 is rho S0. Okay, this is one assumption, that initially the system and the bath, they are decoupled at infinite time in the minus infinity time, minus infinity in the past, the two are decoupled, and then I bring them in contact and let them evolve, and at a later time I am asking how does the system, this is in this sense, this is just the system one. Okay, so this is one simple assumption that I can do, but then I have to make more assumptions, because I have to somehow separate out the dynamical evolution of the system and the bath degrees of freedom, because if both are evolving at the same time scale, so then to know the bath I need to know the system, and to know the system I need to know the bath. So how do I do? So therefore I have to do a time scale separation. Typically what you say is that the bath is always in a stationary state, and bath has already done its job. Universe has already settled down to wherever it had to settle down to, while I am still evolving. Okay, so that leads to this an equation for the reduced description of the system. This is the description for the system density operator, and obviously the effects of the bath come into this equation as some effective terms. It is the same philosophy that you take while discussing Langevin equation. Okay, maybe you have done, maybe you haven't done. Let me anyways ask you. There is a phenomenological derivation of Langevin equation due to Zwanzig. Okay, Zwanzig did it for the quantum case, but how many of you do it? You take a harmonic oscillator which is interacting with a collection of harmonic oscillators. These harmonic oscillators are not interacting with one another, but the system oscillator is interacting with each one of them. How many of you have done? This is the only phenomenological derivation of Langevin equation that one knows of. You have done it, right? So it is similar approach. Okay, why do you do harmonic oscillator? Because you can solve those equations exactly. So here it is somewhat similar. So does that answer your question? Okay, fine. Okay, so the effective description of the system is given by the Lindblad equation. So let me write down the Lindblad equation. In fact, this way of deriving the Lindblad equation is what you will find in, where will you find it? Definitely this one discusses it. It's a rather lengthy derivation, but in the notes I have given a back of the envelope calculation. And since back of the envelope has only limited space, so the derivation is also limited in its details. Okay? Okay, so now I have to write down some effective terms here that model the effect of the bath on the harmonic oscillator. Before coming to that, you now understand open and closed? We are open systems because we are always interacting with others, okay? I am not isolated. I will become isolated if I lock myself in a room. COVID was kind of closed system, no? Everyone was locked up in the, okay? So open is you are exchanging energy, talking to others, exchanging notes, books, WhatsApp messages, whatnot, okay?
Very impressive, I have a question.
Yeah.
Can you write these sentences generally, or it is related to a specific problem that we want to solve?
It is related to specific problem because you have to tell me what is the microscopic process that you are trying to model by coupling the system with the bath. Okay? For example, just as in the Langevin equation, I know what is the microscopic process that I want to model. I want to introduce dissipation, and the dissipation term is linear, so it is x dot. So I know, it's not a completely general equation. I have to model it. So here also I need to model it. Okay. So how do I model? Does that answer your question?
Yes.
You can write down. You see, symbolically you can write down. But then, what is the precise form that this equation takes up depends on what is the precise process, nature of the dynamical process that you want to model.
So now you want to write these sentences just symbolically, and after that?
What I will do is that I will take some particular dynamical processes and tell you how do you write this equation, and you will at once know if you make a different choice how to write down the equation. Okay? So what is the process that I want to deal with? Okay. So let's first take the example of a harmonic oscillator, quantum harmonic oscillator. So a quantum harmonic oscillator, let me now forget about S here because I understand that this is the Hamiltonian of the system, this is the density operator of the system, and I want to introduce the effects of the bath on the system through some effective terms here. So what is the Hamiltonian of the quantum harmonic oscillator? Okay, this I guess you know, where there are some basic properties. For example, first I define these energy eigenstates. H acting on n will give you n plus half h bar omega of n. So these are the energy eigenstates, and A is the annihilation operator. A acting on n is equal to square root of n times n minus 1, and A dagger acting on n plus 1 times plus 1, and A dagger commutator is equal to 1. A question for you. A dagger commutator is equal to 1. These two are operators. Why do I write 1? How can two operators, when I take the product, I get a 1, a number on the other side? But in textbooks, they always write it as 1. Is the question clear? These are operators, no? These are matrices. When you multiply matrices, you should get a matrix. You should not get a number. Why do I get a number? Identity, that's right, absolutely. But you write it as one, okay? And why, there's another trick question that we often, suppose you take the trace of both sides. Huh? So trace of AB, I know is trace of BA, cyclic property. So therefore trace of A dagger is equal to trace of A dagger A. So the left hand side gives me 0. But the right hand side can never give me 0 because it's an identity operator. If I take that trace, definitely I won't ever get a 0. What is going on? Is this equation not correct?
I think this is not correct in quantum.
No, it is an equation, these are matrices, nothing to do with quantum. So what I do is that I go to a representation. I choose a... But trace of AB is equal to trace of BA.
But like you have to first find the matrix and then
I find the matrix, yeah, I'll do what you ask me to do. I'll choose a basis and then I'll express A as a matrix and A dagger as a matrix. I'll multiply A dagger, take the trace, I'll multiply A dagger A, take the trace, and I know that I'll get the same answer because trace of AB is equal to trace of BA. No, certainly no, it cannot be. If I do this, what I get? I get A dagger minus A dagger A. So, trace of, if I do this, I should get 0. See, trace I can, trace means what? Trace means I just have to put n here and sum over n. This is definitely not the... See, the thing is that this cyclic property, it holds only for finite dimensional matrices. If you take infinite dimensional matrices, it will never work. You can try it out. What you do is that you write this as a matrix and this as a matrix, take the product. If there are infinite dimensional, there are two infinite series. You cannot just change the order because this means that you just change the order of the two summation. This will not work if you have infinite dimension. These are infinite dimensional matrices. So cyclic property of trace holds only when the matrix is finite dimensional. So therefore this is okay. This is not equal to 0. And so is that. There is a nice book that probably in Matthew's time was very popular. Now I don't think it is available. The book by Whittaker-Watson. Whittaker-Watson, this analysis and mathematical analysis or something. Very old book. I mean, old meaning really old. I mean, older than oldest. Okay. So where they discuss all these funny properties of. But anyways, okay. So coming back to here. So this is this. So this I can, you know these things, right? This ladder operator, this creation, annihilation operators and so on. So this I can interpret it this way. By the way, these are operators. I am not putting the hat. Sometimes I forget some. Okay. How do I interpret it this way? I interpret it as though like this nth energy eigenstate has n quanta. N number of quanta which I may call photon, phonon, whatever. Each one of them has got energy h bar omega. So therefore, when I am in the nth eigenstate, I have n photons or phonons or whatever is your favorite quanta of each of energy h bar omega. So therefore, when you are in the nth state, you have n photons. Each one has got energy h bar omega. What is the total energy? N times h bar omega, which is n times h bar omega, and this half h bar omega is the quantum correction, 0 point energy. So it's just a shift that you can forget. Because even when you are in the ground state, when n is equal to 0, still the ground state does not have 0 energy. Why the ground state cannot have 0 energy? In classical mechanics, ground state can have 0 energy. In quantum mechanics, you cannot have due to something. No, because of the uncertainty relation, that you cannot make x and p simultaneously 0. Yeah, because xp commutator is I h bar. Classical mechanics, I go to the ground state and which has 0 energy by putting x equal to 0, p equal to 0. The particle is at location x equal to 0 and it has come to a standstill. The velocity is also 0. But here I cannot make both the position and the velocity simultaneously take up the value 0 because of the uncertainty principle. So I have n photons, each of energy h bar omega, and if I do the dynamics of the closed quantum oscillator, that is, if I prepare the system in one energy eigenstate, I am going to remain there forever, right? Sure? If I prepare the system in one energy eigenstate, I am going to remain there forever when the system is closed, right? Because it's unitary evolution. So this, the state, if I prepare the system in this eigenstate, I will remain there. The only way I can come out of the system is if I make the system interact with a bath. Because what the bath may do is it may add photons to the system or take away photons from the system. If it adds photons to the system will jump to a higher energy state. And if it takes away photons, it will go down. So what I am going to do is I am going to write down some effective terms here which will do what? Add photons or take away photons. Is the picture clear? Okay, so let's see how does and I claim that this term is one photon gain term. I'll explain what does this D symbol mean. And this term is 2 photon loss term. Let me write down the form of D, generic, what is the form of D? These are known as jump operators.
These are commutators in the second or third term?
No, this is more complicated than that. So D of O, sorry. So D of O acting on rho is by definition this guy, 2 of O rho O dagger minus anti-commutator. This is just a shorthand for writing this guy. 2 of O rho O dagger minus O dagger O rho anti-commutator. First let us see why do I need this term. Does it preserve the trace to be equal to 1 at all times? Can somebody quickly check that the trace remains equal to 1 at all times if you do D of this sort? Let's do it. Trace of rho here, okay, here I will get 1, no problem, because trace will act on this and this can. What about this guy? If I take trace of this thing, do I get 1? Trace of O rho O dagger minus trace of this guy. Let's do it. So trace of 2 times O rho O dagger minus trace of O dagger O rho minus trace of O rho O dagger O. What I am doing is that I am running the trace operation on this equation. Okay? So this one will give me 0. Why? because trace of h rho minus rho h, that will give me 0. So this term will, so I just need to ensure that when I run the trace operation here, I should get 0 and I should get 0. So therefore this would mean that del t of trace of rho is equal to 0. That is to say that trace of rho is equal to 1. Okay. How do I check that this is equal to 0? This is trivially equal to 0 because these two guys are exactly the same. Because of the cyclic property, so you get a 2 factor and the 2 factor cancels with this. Because this one will be rho O dagger O, rho dagger O, so you get 2 and then here also you do the cyclic. So therefore this equation is at least correct in the sense that it preserves the trace to be equal to 1. Huh? In the?
You just said that the series of trace doesn't hold in infinite dimension.
Yes, I did say that. Let me see how I can escape from there. I guess certainly if I limit the Hilbert space, it is, let me say, okay, let me put it this way. I think what the theorem says is that it is not guaranteed that always, trace of AB is equal to trace of BA when you are dealing with infinite dimensional matrices, unless the series, the infinite series that you are dealing with converge. Okay, and if it is a convergent series, then it is fine. I will try to look up the proof once more. Okay, but anyway, so this term, it actually preserves a trace. How do I know that this is 1 photon gain and this is 2 photon loss? What?
Can I ask a question? Why you interpret the interactive terms as giving and taking photons? I don't understand.
No. This is an example. Okay, this is an see the bath that the system is interacting with will either add photons or take away photons. What else can it do? Because I am in an energy eigenstate, so it has a certain number of photons, and when I let it interact with a bath, it will either take away photons or add photons. You may say why, or it can only add photons, that is also fine. It can only take away photons, that is also fine. But it can only change the number of photons in the system. This is the simplest dynamical process that I can think of.
This is just an example.
This is just an example. Okay, the system is in a given energy eigenstate with n number of photons and it is interacting with a bath. So what the bath can do is change the number of photons, and it can change it in many different ways. It can add 75 photons and take away 52 photons. It can only keep on adding photons, not take away any photons. Why I do both a gain and a loss term is because this will allow the system to have a stationary state. That is the reason why I want to do it. But this is just an example. Let's first understand this example and then we will go to your favorite models for the dynamical processes and see how do they look like. How do I know if I am given an equation of this sort, how do I know that this is really a 1 photon gain term and this is a 2 photon loss term? Because this doesn't look like, okay, I can understand that this creates something because there is one A dagger, so perhaps it creates one guy, and this is a, I'm sorry, A square, so perhaps it kills something, and it kills two guys at a time because there is a square factor, there is a 2 factor there. But what is a better way to do it? I mean, is it, what can you do if you are given an operator equation of this one? What do you do? Because with this, the best thing to do is to write down the corresponding master equation. Reduce this operator equation into an equation that deals with just C numbers, just some classical numbers. So what I do is that I take this equation and then I find its matrix element between state this. what will it this what will this guy give me? Can somebody tell me? Rho is a function of t, by the way. Rho this what is it by definition? This is the probability for the system to have n photons at time t. No? Because look at the definition. Rho generically, how does it look? Rho looks like this. Okay, so that means if I do psi j, rho psi j, what do I get? I get pj. No? This was the definition of our rho. If the system is in a mixed state, so this is the probability to be in this state, sum over I. So therefore, when I take the matrix element of rho between psi j, these are orthonormal. Okay, they form a complete set of bases. So therefore, I get pj. So therefore, the matrix element, the diagonal elements of rho would give you the probability for the system to be in the corresponding state. The diagonal element of rho gives me the probability to be in the nth energy eigenstate, that is the probability to have n photons in the system. Right? So is this definition clear? That's what the diagonal elements of rho give you. This is from the definition of rho. So what I do is that I take this equation and I multiply from left by bra. So I multiply from left by bra n and I multiply from right by ket n. And I just evaluate this. If you do it, then of course the left hand side will give you this. This term will give you 0. This term will not contribute. While the second term that will give you now everything becomes very clear. This is the Lindblad equation for the time evolution of the density operator of the system. Here I have put in by hand two terms that arise due to interaction of the system with the bath, and I have taken two examples. Okay, these are example terms. I just want to learn how do these terms behave. So I put a term which is like this and I put a term which is like that, and I claimed that the first term models 1 photon gain and the second term models 2 photon loss. How do I know that? First of all, I check that if I have an equation of this sort, it preserves the trace. Trace is always equal to 1, which is good. Secondly, how do I physically interpret these terms? So what I do is that I take this equation and I act on it from the left by the I sandwich it between the bra and a ket from left and from right, and I know that if I do it here, I will get the probability for the system to be in the nth energy eigenstate, that is to say the probability for the system to have n eigenvalues, n photons. I just do it here. This term will give me 0 if I do an n here and an n there. This you can, this is also physical, because if this term had appeared here, then I would have been in trouble. Why? Physically? So first of all, do you see what am I doing? Why this term, a contribution from this term cannot appear here? No, it's not n oscillators to n plus 1. Oscillator is 1. One oscillator may have many different photons. It could be in the first energy eigenstate or second energy eigenstate or third energy. If it is in the third energy eigenstate, I use a different language. I say that it has 3 photons. If it is in the second, I say 2 photons. Okay, there is just one oscillator at the moment. Okay, just one single quantum harmonic oscillator with frequency omega. Okay. So if this term appears here, it would mean that the number of photons in the system changes under unitary evolution. That cannot happen. Why? Because the unitary evolution is going to keep the system in an energy eigenstate forever. If you prepare the system in an energy eigenstate, unitary evolution cannot take it out of that energy eigenstate because it's an eigenstate of the system. Right? So this term doesn't appear, and you can check mathematically. What you do is that you write down h you know what it is h bar omega of a dagger a plus half. So you just plug this in here and you do this thing, you will get 0. Now the second and the third term. So this requires to do some simple algebra. You know how d of a dagger rho look like. So d of a dagger rho would look like 2 of, I keep forgetting the order, o rho dagger. Minus of commutator a dagger comma rho. It just use the general formula that I just wrote down. D of O dagger rho is 2 of O rho, D of O of rho is 2 of O rho O dagger minus whatever. So you have to do this algebra, but now let us look at this equation and it will be at once clear why this is a 1 photon gain term and this is a 2 photon loss term. Why? This is the form of a master equation, the master equation that we are all very familiar with from stochastic processes. What I am asking here is, how does the probability to have n photons in the system change as a function of time? How can the number change? The number can change only when you absorb photons or you give away photons. Okay? What is this term? Let's forget about these for a moment. Okay, so let's say I did not know that this is the gain term and this is the loss term. I am given this equation and I compute the matrix element and this is the equation that I get. And let's see if I can interpret these terms physically. In order to have n photons in the system, one possibility is I started off with having n minus 1 photons and then I absorb 1 photon. So n minus 1 plus 1 will give me n. So this is a gain term. That's why it comes with a positive sign. Or I started out with n photons and I absorb 1. So I have n plus 1 photons. So I lose probability, minus sign. Right? This is how master equations are written, right? There is a gain term and there is a loss term. Gain, when you gain in probability, you gain not in the number, you gain in probability. So this is the gain term because n minus 1 absorb 1, you gain in probability. N and you absorb 1, you lose probability. So certainly this is the 1 photon gain term.
And how can we interpret the coefficients n and n
Okay.
plus 1?
Okay, these comes if these coefficients, they appear when you do the, here what happens is that because of the structure that I have chosen, the coefficients just tell you that the rate, you see gamma 1 is the rate, okay? Gamma 1, what is the dimension of gamma 1? Sorry. Gamma 1, what is the dimension? Huh? 1 over time, right? Right, it's a rate. Why? Because this is the structure, you know how a master equation looks like. A master equation has this generic form. How does a master equation look like? A master equation has this form what is the probability that I am in configuration C at time t, and how does it change? So there are two terms, one in which you were in some configuration C prime at time t, and in a small time dt you jumped from C prime to C. So this is the gain term. This is the first term, this term, okay. And then there will be a loss term. You were already in configuration C at time t and you jumped out of C to some other configuration C prime. Okay. So, this is the gain term, this is the gain term. Gain in probability, and this is not gain in number or anything, gain in probability term, and this is the loss in probability. Okay. So indeed, it has exactly this structure. This is the gain term, loss term, gain term, loss term. What about the coefficients? The coefficients tell you, because you have factor of n and n plus 1 here, the rate, this gamma 1 n, this is going to be the rate, W. Rate meaning the probability per unit time to jump from one state to another, n minus 1 to n. It just tells you that the rate is not a constant, it depends on the number of available photons. Okay? See here, nobody told you that this has to be a constant. Typically, how many of you have seen this equation? Random walk, I think you have seen this, right? This is this equation, you have detail balance when it goes to a stationary state and so on, okay? Does that answer your question? That the rate of transition depends on the number of available photons in the system. What is the number of available photons? N minus 1 to start with, and it gained 1 photon, so n. N to start with, it gained 1 photon, number of available photons is n plus 1, n plus 1.
And this dependency is because that you have already defined that
This is an example that I have taken. I can take another example. I can say that, but gamma 1 is not a constant, it is something, some independent. So this is, I just want to show that for this equation, if I give you this equation, how do you interpret the different terms? And then you can play with it. I can make this one, instead of a dagger, I can make it a dagger to the power 56. This would mean that I absorb 56 photons. And then you will have a term n minus 56, n plus 50, n 50.
this is just a specific interaction between
Specific interaction. The point that I want to emphasize or impress upon you is the following, that you see the form of the Lindblad equation always has to be such that there are these jump operators appearing here, and a jump operator has generically this form, d of I keep writing O of rho is equal to O rho O dagger minus 2 minus of O dagger O. These operators have to be of this form. Now what you put for O is entirely your choice. It is the kind of dynamical processes that you want to study.
What does that plus mean?
Plus anti-commutator. Okay, so AB plus, I thought it is AB plus BA. Okay. Let's look at the, so this term is indeed 1 photon gain term, and it is easy to see that this term is 2 photon loss term. Why? Because to gain in probability, I have to start with n plus 2 photons, and I give away 2 photons. So then I jump to n, I gain in probability. Or I am in n, and I give away 2 photons, so I go to n minus 2, I lose probability. So now you see, what you have to do. Suppose you want to, this is 1 photon gain and 2 photon loss. Suppose you want to have 55 photon gain and 76 photon loss. So you have to put the power accordingly there. And in the case of harmonic oscillator, this is the simplest dynamical process that I can think of. What you can do is that if you want to make them interact with a bosonic bath, let's say, okay, a bath of photons which is in equilibrium at a given temperature, then what you do is that you make these quantities temperature dependent, temperature of the bath. So, this is a generic form, and then you can do whatever you want. Given this generic form, you can play with it completely. No, nothing. See, if it is 0 or non-zero, it will be contained here. See, the temperature of what? Temperature of the bath. So I can make these guys function of temperature. If the bath is in equilibrium at a non-zero temperature T, so then I know I can write down these terms explicitly in terms of the temperature of the bath. Now, why do I do 1 photon gain and 2 photon loss? Okay, so I do it because I want this to model a van der Pol oscillator. Okay, so let me go there, but before that, let me pause and ask if there are questions. Oh, it is already almost the time, but I can show some picture. Leah, so we need to discuss this, no? Okay. So maybe we send them an email, maybe, okay. So I'll talk to Leah and tell you.
And it will be also on this quantum part or
Okay. So now you are getting into microscopic details. Now you say it will be on quantum part. So shall we do chapter 4 and 5 or maybe chapter 4 section 4.2 and equation 46? I will not keep it a mystery, but it will not be so difficult that you would like to jump into the sea, nothing of that sort. So that I can assure you. Are there questions on this part? Not the exam part of the quantum part, but the non-exam part of the quantum part. So since let's do it tomorrow because I'm already, time is over. How many of you know about Wigner function? Because I need this concept of Wigner function. There is something called, not the Wigner distribution, there is something of Wigner distribution, but Wigner function, which is the classical analog, quantum analog of classical phase space density that you write for quantum systems. You don't know, so okay, so we'll do it, okay. Because, okay.
Could you please explain again for me why the linear summation between the different initial conditions does not work in mixed state?
Okay.